So my presentation is going to be about really what I do here in Hawaii. Okay, sorry, it's not. I arrived in Honolulu at the beginning of November 2001. And I've been hired by Professor Steven Businger as a postdoc in the Department of Meteorology at the time. And after about a year, actually, I started working for the just founded, like was really new at the time, Mauna Kea Weather Center, which is as a research meteorologist myself. What is the Mauna Kea Weather Center? The Mauna Kea Weather Center is a project that was born with a memorandum of understanding between the University of Hawaii Meteorology and the Institute for Astronomy. And there was July 98 at the time when this idea was born, and with three main objectives in mind: provide custom weather forecasts to the Mauna Kea Observatory, determine the meteorological condition that provide the best astronomical observing condition for them, and of course, convey and communicate all this to the astronomers through forecast data and imagery, making them available for them. So basically anything that could help the astronomers making their observation time, optimizing their observation time, and supporting their activity. Why and what kind of forecast the astronomers need? Like in the usual, for the usual public, making a prediction in terms of weather means like predicting when bad weather is coming, so that you can prepare for it. In this case, actually, we want to predict good weather, and we want to predict how good the weather is actually going to be, and why. If you look at the image that it's on this slide, this is an image of the telescope Gemini North, and during at the beginning of the evening, when they are starting observation, when they open the dome that it encloses the telescopes. And you see here, it's actually in the process of opening. You see that the mirror at the very focus of the telescopes. And then you see that the vents, the apertures that are like at the bottom of the dome, they're actually being lifted so that the air can flow through the dome itself. But those mirror can actually be very sensitive to changes in temperatures, and so they can actually vibrate when the temperature, say, is when it's colder, for example, outside than was inside the dome before the dome was opened, or the other way around, if outside is warmer than inside. So what the astronomers want to do, they want to know ahead of time what the temperature is going to be outside of the dome, so that they can prepare the mirror, they can warm it, that they can cool it, and in a way that they can avoid the transient times of during which the mirror tends to adjust. And adjusting means vibrating. Vibrating for a mirror means any image that you would acquire through it would be blurred. So temperature, for example, is something that you want to predict with quite an accuracy, like with at least a degree precision. Then, of course, wind can also impact the observation, because more winds means more turbulence. More turbulence means blurred images. And also, you want to avoid certain kind of shake. So you want to prepare for winds as well. Clearly, cloud can be a problem because you won't be able to see through if you are making observation in the visible range. Fog and moisture can also be a problem for certain instrumentation. Other instruments can actually make observation through moisture. So what we try to do is tell the astronomers, okay, there is going to be a patch of moisture coming by tonight. So the astronomers can actually use the observing time better, meaning they can schedule their observation depending on the weather conditions. They can optimize the instruments that they're using. So an instrument that is more that is capable of working in moist conditions will be working when there's those conditions happening, and instruments that actually need dry condition will be working at a different time. And this is quite important because the observation in a telescope needs to be scheduled ahead of time. If the astronomers are able to optimize their observing time, it means that they actually save money, because these instruments are quite expensive to operate, and any time that you can use, so maximizing actually the time that they are, the dome is open and the telescope is acquiring data, that means actually you're saving money. Then of course, the last item on this list is optical turbulence. And that's something that I will explain you better with the slide later on in the talk. Then of course, clearly you also need to warn them if there are going to be any weather hazards coming by, like anticipating high winds and further precipitation. It can snow on Mauna Kea, and it can be hazardous for the technicians or the ranger to be up at the summit at the time. So they want to know when these conditions are actually happening ahead of time. And so this is our part of prediction, which is the usual weather prediction. Everything that we do, it's summarized on our webpage. Perhaps some of you know or are familiar with this page. I'm probably some won't, but if you go to this website, mkwc.ifa.hawaii.edu, you can see everything that we do, and all the data that we gather, we post them on this website. If you go on our webpage, you can sort of like see right now what's going on, and we're going to do this actually together. I'm going to show you what's actually happening right now. So can you see my screen right now, Chiara?
Yes, vedo il sito web.
Okay, great. Okay, this is the page as it is right now. And you can see here right at the corner that at the summit right now, the temperature is 4.5 Celsius. Relative humidity is 37%. And the wind is 7 miles an hour from the northeast. We can actually have a look at what's going on up there. These are webcams that are in various places at the summit. And you can see that actually it's clear and it seems to be dry. 37% of moisture, actually, it's not super dry. When it's really good, you see things like 5%, less than 10% moisture there. So it's really, really dry. And that means it's really, really good for observation. On this webpage, we gather satellite data, for example. So you have infrared data. You can see that right now the weather over Hawaii is really nice. I believe if we overlay model data on it, that we have like a area of high pressure, and so we are going through a patch of good weather. If we look at this channel, this is the water vapor channel. We can see how the water vapor moves around over with a loop of about 12 hours. So the past 12 hours up to now, this is what's basically the latest information that we have. If you want to see where it's raining, then you would go on a radar page and you would see with a composite here, like where it's raining. There is not much going on right now. You see the usual showers from trade winds, more on the east side of the island, but there is not too much happening right now. So it's good weather for everyone and a good weather for the astronomers. Every day, the forecaster looks at this data, look at model data. This is another important part of what we gather. The National Center for Environmental Prediction runs every day, 4 times a day, is a global model global model, which is called GFS. And you can get these data. They're public. They're available for everyone who wants to use them. And you can see, for example, I don't know, we plot here the Central Pacific area, or like actually the entire Pacific. For example, this is like the model, the global model over the Pacific is actually has in storage for us for the next 10 days. So if we start from the very beginning, from today, we see that this is precipitation. This is the precipitation map. You see that there is not much precipitation over Hawaii. There are only the few little bubbles that are typical for trade winds showers, and which means it's decent weather. Maybe there is something happening starting from these days, which is next Tuesday. Tuesday, Wednesday is when we should have a little front coming by, and so maybe bringing a little bit more rain. This model, it's a model that it's has a coarse resolution, which means solves the equation of motion over a grid that is about 25 kilometers large. So imagine to have like a grid all over the world with a resolution of about 25 kilometers, which is pretty good. But for our application, it's not quite enough. So what we do, and this is where actually I come in, and if we go back to our presentation, my main task at the Mauna Kea Weather Center is to run and maintain a high resolution numerical weather prediction focused on the Central Pacific area. So Hawaii and just like a little square around Hawaii. And I made a little visual sketch to let you understand how actually what I do. I get the data from the global model, and I sort of interpolate it back over a grid. Over a grid on a smaller area, just focusing over Hawaii, and I basically make a grid that is has a resolution that it's a lot higher than the global model, and I go down. I start at 4.5 kilometers. I solve basically the equation of motion within only this box, and basically I'm able to come out with plots that now have an accuracy that is higher than the global model. I'm not going to go to the details of this because it can be a little cumbersome and a little boring too, maybe. But we run a model with a grid that is 4.5 kilometer grid over this large area. Then we zoom in. We are able to go down to 900 meter over Big Island, and then we zoom in more over the summit at 300 meter. So we want to go down and down in resolution because means we are trying to get more and more details on small scales of what's actually happening around the summit of Mauna Kea. So while we gather what is going on around the islands in general, then we try to focus on what's actually happening at the summit of Mauna Kea. And this model output things like the high level clouds, like you see in this little loop here. Okay, and actually, if we go back to our webpage, this is the little button you want to push, WRF, to see the output of the model that we actually run locally for the Hawaiian area. And for example, if we want to see, I don't know, a cloud cover, mid-cloud cover for the next 60 hours, then this is the result of the model that has been running. This is from the model that ran like midday today. So this is the prediction for the evolution of cloud cover for the next 60 hours. If you want to see what's happening over Big Island in terms of precipitation, for example, then we go here and we see how the precipitation is going to evolve over the next 60 hours. So if you want to see, for example, tonight, 5 p.m., this was like just about an hour and a half ago, and this is going to be 8 o'clock, 11 o'clock. Actually, sorry, sorry, I'm a little behind. So this is 8 o'clock tonight, on the 29th, and you see there is like rain, little rain, not too much, but below the summit of Mauna Kea, Mauna Loa. And then you see it's completely dry, 11, and 2 at night is even less rain around, and so on. So this is also another tool that allows us to come up with a prediction for the astronomers for the next night, for the next few nights. And all that we do, all this data that we have available on this webpage actually get summarized in the forecaster forecast. So every day by 10 o'clock in the morning and by 5 p.m. in the afternoon, you would see that this page gets updated. And you have here a narrative of what's going to happen tonight and for the next 5 nights. And if you want to have a quick look at what was the latest forecast from the Mauna Kea Weather Center forecaster, you have this plot that summarizes quickly what's going to happen. So, for example, if you look at the very top of this plot, this plot says that for the next 4 nights, there is no risk for fog and precipitation. Maybe something is going to happen around late on Monday and through Tuesday. This means like the probability of having fog and precipitation is going to increase some. The skies are expected to be quite clear throughout at least the next 3 nights, and then maybe some clouds are going to build up starting on Monday. If you look at the temperature, you see that the minimum temperature is actually quite warm, 2-3 degrees Celsius. And then maybe there is going to be a decrease in temperature on Tuesday, when it's going to be 1 Celsius and maybe decreasing even more. This line here shows like the total amount of water, which is in the layer of atmosphere from the summit of Mauna Kea all the way up. And it says that the total of it would be 5 millimeters, tonight, but then decreasing over the next 3 or 4 nights. And it's going to be, like Saturday and Sunday look like they're going to be quite nice in terms of relative humidity going down. The very bottom of this plot shows the wind. So light wind throughout the entire time, not much wind, like 5 to 10 miles an hour. So ideal conditions for wind. And then there is this stripe here that actually shows an indicator that summarizes the turbulence for the summit of Mauna Kea. And what it's saying is that the next 3-4 nights, it's actually pretty good in terms of turbulence. Like when we get these values below 0.5, 0.6, it means very good. And then most likely it's going to degrade and get worse as we go toward the middle of next week. So this is sort of like what the astronomers look at before starting their observation. But then I mentioned turbulence, right? As one of the products that we provide to the astronomers, prediction of turbulence. But what does exactly entail, and what exactly is? What I'm going to refer to often is the concept of seeing. And what is seeing? Like one way to explain it, like you have to imagine that light is coming from a very distant object from space, and they are getting closer to the Earth, and you can imagine them as a very uniform wavefront, so light that is undisturbed. But when they cross the atmosphere, they also cross pockets of cold air, warm air, air that is in motion, and that creates like what is called like optical turbulence. And basically the wavefronts of the light coming in are distorted. And the results of this is that any image that you would acquire from Earth is actually going to be either blurred, or you will see scintillation for this object that you are observing. And if you want to relate this concept to something that is closer to us, it's the same idea of looking at inside a swimming pool. And with the water that is in motion, you will see that the tiles of the swimming pool, they look like they are distorted. They are not straight as they actually are. And this illusion is actually due to the fact that lights travel through water, but this water is in some kind of turbulent motion and creates this effect. Same things happen to the light that travels in space, but crosses the atmosphere before getting to telescopes or to even just a naked eye. And again, if you want to get this concept in terms of astronomical idea, like if you are on an island, for example, and you are on the site A, then you see that if you are on the site where the laminar, the flow of the atmosphere wind is sort of laminar, like uniform, you are likely to see the astronomical object has a crisp object, like you are likely to make a nice observation. If you are on the side of the island where actually the atmosphere flow in a turbulent manner, then you're likely to look at something that is blurred. And so what the astronomers want is us to predict the conditions for which you actually are on the good side of the island. I mean, when you have the condition for which their observation is actually going to be optimal. Now, the physics behind all this is kind of complicated. I just put here some equations to give you an idea, but it's actually, even those equations are a simplified version of what's behind this concept. What we want to just, the idea that I want to just try to convey to you is that this thing is going to tell you, it's going to describe the smallest, the size of the faintest object that you can possibly see. So imagine, for example, you have two stars very close. Typically, they are binary stars. So two stars that are actually rotating, revolving around each other. And if a telescope is, or your eye is strong enough, you can distinguish the two stars. But if the telescope is not strong enough, or if you have a lot of turbulence in the atmosphere, those stars can actually sort of like collapse on each other, and you, instead of seeing two, you would see one. So seeing is actually it's an indicator to measure whether you can resolve very close objects. Or another way to say is, what is the size of the faintest object that you can resolve? Seeing is measured in arc seconds. Arc seconds is 1 arc second is 1 over 3,600 of a degree. So something really, really small. And again, in order to give you an idea of what I'm talking about, this is an image acquired by the Hubble telescope, which is actually telescopes in space. So for it, most of the atmosphere is behind it, so it wouldn't be a problem. And it's looking out in space with very little interference from the atmospheres. And so you can acquire images like this one, and this image has a 0.1 arc second thing. 0.1 is very small number for as thing is concerned. A simulation, I'm going to go through now to a simulation of the same images, but with worsening values of seeing. Worsening meaning higher values of seeing. The higher the values of seeing, the worse is the image. So if you go from 0.1 from 0.5, we see that the image is starting to get quite blurred. If we go to 1 arc second seeing, you see we lost a lot of definition. And if we go even further, the image gets really blurred. So even 1.5 arc-second seeing is actually not a good value for this parameter, for this indicator. If you go the other way around for this galaxy instead, this is a galaxy observed with 1.5 arc-second seeing. This is with 1 arc-second seeing, 10.5, and finally 0.1 arc-second seeing. So the lowest is this value, the better the telescope see. Now for Mauna Kea, the average seeing for throughout the years is 0.55. And that is actually Mauna Kea and Chile are pretty much the best sites for astronomy in the world. They are very, they're blessed with optimal conditions for ground-based astronomy. And you might wonder, if we can observe things from space, why do we bother having a ground-based telescope? But in space, you can only put very little mirrors in a telescope. So and you are limited with the observation you can actually do. While with the ground-based telescopes, the mirrors are larger, which means the larger the mirror, the more light you can acquire, the furthest away you can see. So if you want to look at things that are very, very far, or in other way, very, very distant in time, then you need like a larger mirror because you need to collect more light. One more effect of the turbulence in the atmosphere is scintillation. So not just blurring, but this flickering that you see in a star, which is the twinkling, of the star. This is Sirius going through part of its orbit through the night. And like you've seen this probably many times, just looking at the sky, that you see the star twinkling, which is a very poetic concept when it comes to putting kids to bed with lullabies, but it's actually something that is not good for making observation because it's an illusion and it's not due to the star itself. It's due to the medium that light is going through to get to your eyes. So it's something that is due to the atmosphere, not to what it's really happening at the star or in the star. Now, this part, I'm just going to go quickly through it because it's scientific and more boring, I guess. But it's just to say that we have an algorithm within our model that can predict or tries to predict optical turbulence and therefore seeing. So on this slide here, you have the observation in red and blue of last night, what was observed last night in terms of seeing. So you have something that went from, it's been variable around 0.6, maybe sometimes less, all the way down to 0.4. And last night was a transient night from a bad night the day before. And yes, there was a night of observation, but things were still a little bit not optimal, just about average. And the model predicted that last night was going to be a decent night, so we were happy. We can produce maps like these ones of seeing three-dimensionally, so not going to get much into it, but the summits look like they have, the lowest values of seeing, of course, are at the summit, and shows how it evolves through time. And then we also apply some machine learning algorithms, so in artificial intelligence, to predict on average what the observation in terms of seeing are going to be like for the next few nights. So for example, last night algorithm said that with these black dots, that there was a probability close to 1, so that last night and the next 4 nights are going to be good observing nights. And this indication tells you what seeing is going to be like. So last night was an okay, maybe less than average. That's what the model predicted. Tonight is supposed to be a quite good night, actually an excellent night for observation, and then slightly less for the next 3 days, but still pretty good because this is like the average value of seeing on Mauna Kea, 0.55. So this is all good. It means like for the next 4 nights, the astronomers are going to be quite happy. So by knowing in advance the expected weather and turbulent conditions, the astronomers can optimize their instrumentation. more so nowadays that these telescopes are actually equipped with adaptive optics systems. And if you want to get an idea what these are like, you can, if any of you has a fancy camera, you know that there are like now in the new digital cameras, there are systems for the camera to stabilize the image, particularly when you are trying to capture something that is really far from you. You can stabilize with, you know, when you zoom out, you can stabilize the image. Well, the telescopes can sort of do the same things actually at a even more sophisticated way. They can adjust to the turbulence condition, more so if they know in advance what the average turbulence condition for that night are going to be. So they can adjust the images, making them better, reduce the degradation that turbulence is actually otherwise producing on them. So and so we are here, like this our project is such that we try to tell them when it's going to be bad weather, when it's good weather, how good the weather is going to be, and we're trying to tell them the quality of the observing conditions for a given night. So it's going to be very crisp, very uniform, very laminar, very stable, or there is going to be turbulence around instead. And so they can prepare and they can schedule their observation according to what we have predicted. So that's basically what we do in our project. And if you like, I have a couple of videos that I can perhaps show. Let me see what the time is. Well, I'm going to show you one, and then if there is time, maybe we can show another one as well. But this is a video, like 3 minutes about, and it's going to show you what a night is for an astronomer. And please let me know if you can hear the sound or not.
Yes, we possiamo.
Okay, great.